Well, good morning, everybody. It's a great pleasure to me to have Roland with us today. We know each other for a long time, and it's a great pleasure to meet him again. I think you have been here 2 or 3 times, don't you, in São Paulo with
Yes,
Mocha
yes.
workshop? Yes,
Two,
it was.
two or three times. I really can't keep track if it's 2 or 3 times. Yeah.
Yeah, but maybe we can talk about another MOCAS meeting, virtual
Yes.
meeting. Maybe
Right.
we talk about it later. I'm thinking about it. Let's see. But I
Yes.
just want to give a short presentation about what Roland does and who he is. And he is a chemical engineer by Lund University. And after that, well, he got his PhD degree in Lund, supervised by Björn. And then he moved to a postdoc position in the United States when he worked at IBM. In that time, it was a dream to work with risky machines. And he did a very nice job in IBM. Then he returned to Lund, where he stayed until 2010. And from 2010 to today, he's at Uppsala University. Among his research interests, I can highlight a few of them, but he works a lot with Cholesky decomposition, which is a technique that improves the velocity of the calculations. It's really important. And he also works heavily with bioluminescence and photochemistry. It's the topic of this presentation today. And he also works a lot with mode-state configurational perturbation theory. And there is a paper with Manuela and Luis in Journal Chemical Physics, and I think everybody who should learn about how to do calculations or who wants to learn how to do calculation with mode-state CASPT2 should read this paper. It's very good and very important paper. And recently, he developed a new way of carrying out a kind of mode-state CASPT2 calculations, and he called it the best of two worlds. And at the end of the last year, I think, he published 2 papers about gradient enhanced kriging. It's a technique of optimization. Now we can do single state optimizations and minimal energy path calculations, but not intersystem crossings or conical intersections. Use this it's a kind of a learning machine technique. But he is heavily in software development. He's the author of Seward, and everybody who uses MoPro and MoCAS know how good Seward is. And if you run geometry optimizations with MoCAS and MoPro, you also work with Alaska and IslaPath, and thanks Roland for them. And he's working with MoCAS since the very beginning of MoCAS, I think, and now in Open MoCAS, which is an open program. And he is also among the authors of MoPro. Among his publications, as far as I remember, you are the author of 2 books, Multiconfigurational Quantum Chemistry, Bjorn started writing and the other guy finished it, and it was published in 2016. And by the end of last year, with Leticia Gonzalez, they edited this book, Quantum Chemistry and Dynamics of Excited States. He has around 200 publications with an amazing 13,000 citations, and in this index age around 53. So during this presentation, please keep your microphone mute. But if you want to make questions, you can interrupt him. Just ask your question directly to Roland. and I'm sure everybody will enjoy this presentation. So thank you very much for being with us, Roland.
Thank you very much, and thank you for a very nice introduction. Should I share my screen now?
Yes.
So first of all, I want to show this. I got the book 2 days ago. And it's really a good book. Of course, I'm saying that because I'm the editor now. It is actually a very good book. The second half of it is a lot about different techniques in molecular dynamics. It's really worth to have on the shelf. It has a very good part on perturbation theory, if you like. So let me start by sharing my screen here now. Entire screen. And before can you see my screen now, right?
Yes, yes.
Okay, let's see now.
Screen, not our presentation.
Okay, so first of all, since I have one of the co-authors of this marvelous paper that I've done with Wilhelm, so the lecture today is going to be on a part of the research that was presented in this paper that was published in what's it called? Chemical Reviews. So thank you very much, Wilhelm, for being a part of this. And if I switch,
I thank you for the invitation, of course.
well, it was a pleasure to have you guide us through this. Also, I noted that Igor is here. Are you in Israel, or where are you? Igor?
Yes, I am in Israel, in Jerusalem.
Okay, nice of you to meet up. It must be late in the evening.
5 p.m.
Okay, well, 5 p.m. Okay, you're an hour ahead of us. Okay,
Exactly.
let me start with my lecture so we can celebrate weekend after this. At least I will do that. So wow, did you notice this? The misspell here in the title? Adiabatic. I of course know how to do that. So I'm going to talk about non-adiabatic chemiluminescence dynamic of a very special molecule, a 1,2-dioxetane. And as I proceed, you're going to see how simple and beautiful this molecule is. And we're going to look at how the chemiluminescence change as we substitute this molecule. So let me start by thanking some of the people that have helped me during the years. I sort of identified this problem. Well, I discovered the paper that described the problem a long time ago, and during a course of 5 to 10 years, we sort of been trying to develop the machinery to understand what's going on. And these people here, there's Morgan Vacher, for instance, Ignacio, Hans Carlson, and others that have been helping me. I think you recognize these. This is Alessio, and this is Manuel, and this is Poria. Poria was visiting you a few years ago. So I have a disposition for this presentation. So first I'm going to sort of present the background. What is chemiluminescence and some facts around that. And after that, I'm going to present what has been done up to that point before we did this work. This work was published in the end of 2017. So it's a 3 years old work. After that, we're going to look at dynamics. First, we're going to look at dynamics just on the ground state surface. And then we're going to look at dynamics on both the ground state and excited state simultaneously using a surface hopping technique. And after that, I would like to come with conclusions. And during my presentations, of course, interrupt me at any time and ask questions, please. So background. So what is photochemistry? I start with that. I worked at Willy Sundström's group for a while. They did laser spectroscopy, and this, in a sense, was what they were doing. So they had a molecule on a ground state surface. They shined with a laser pulse on it, excited a molecule, and then they let the excited molecule propagate on the excited state surface, and then they shined on it again and tried to understand what happened here. Usually during a excited or photoinitiated process, you will have that the molecule could radiate back down, or it could do something we call radiationless relaxation, where it goes through a conical intersection, a place where the ground state and excited state surfaces touch. That is, the energy of those two states are degenerate. And at the conical intersection, you could have a multitude of different things happening. You could get back down here to your reactant. This is, for instance, how your eye work, or how a suntan lotion works. It absorbs the harmful radiation, and you come down here and you have translated the radiation to thermal vibrational energy. You could, of course, have that it goes through the conical intersection and produces a product. So you would have what's called photochemistry. Going down here would be photophysics, they call it. And there's the third alternative, and it is that you continue out on the surface here and something else happens. But photochemistry, by definition, is a chemical reaction caused by the absorption of light. You start with light. Now, chemiluminescence is the very opposite of it. At the end of the day, we're going to end up here. We're going to be in an excited state, and we're going to emit light as we radiate ourselves down to the product. What's special with chemiluminescence is that you have a reaction, a ground state reaction taking place on the ground state surface that will go through a transition barrier at which, or very close to, there is a conical intersection. And there's a likelihood that rather than having your molecule continue on the ground state surface, it's actually going to end up through a non-adiabatic process on the excited state surface. And I found it very interesting how from just a conventional thermal reaction could produce a product that is in the excited state without beaming myself up with light to start off with. So this sort of caused my interest to try to understand what happens at the conical intersection, and could I get a more qualitative understanding for why these things happen. Also, chemiluminescence is just an awesome phenomenon. In nature, you have it here, like for instance in this picture, it's a firefly, which actually is a beetle. They use the light here to emit, to communicate and attract partners. But you could also use it, and there are some species that use it to lure prey, or you can also use it to defend yourself if you're attacked. There is, for instance, a shrimp that once it's attacked, it sort of gurgitates up contents from its stomach that is glowing, and in such a way it sort of stuns the one who is attacking it. Also in the laboratory, we're using these kinds of techniques. So here's somebody's doing a demonstration of bioluminescence or chemiluminescence, and it has a wide of application fields in the analytical chemistry. And it's very nice because it's a non-evasive method to analyze things. And I could be talking hours about that or somebody else, but that's not what we're going to talk about today. So I would like to understand this. And of course, I was attracted by how the firefly did it. But, you know, before we go on something that advanced, I think, at least the way I do, I would like to understand the very basic thing. So let's strip this firefly and find what's happening. Well, there is an enzyme, luciferase, with a luciferin molecule. Well, that is still a bit too complicated to understand. Why could you have a chemiluminescent process? So I thought, well, let's look at the substrate. So here we have the luciferin molecule of a firefly. Looks very complicated. I think it's still too big to understand. So we stripped away, and actually the interesting part of this molecule is this part here. And so let's cut out this piece for a while. We're down to this species here. It still looks a bit complicated. We're simplifying it even further and further. And here we end up on something I feel comfortable that the methods that I have today, I will be able to not only give me a qualitative understanding, but also a quantitative reproduction of experimental data. So let's start with that. And then, you know, this guy comes in together with his colleague. And they've done experiments on this. This is just marvelous. So they have been producing these molecules, and they have produced it with different substituents here, R1, R2, R3, and R4. And then they have measured the chemiluminescence, how efficient that is for these different substituted species. And what they found was, the first thing was that it's a triplet excited state that emits the light, not the singlet excited state. So that's a very interesting, because that means there must be interstate crossings somewhere there. Also, they found that as they increased the number of substituents, the efficiency increased more than 1 order of magnitude. Here I have a graph. On this axis down here, we increase the number of methyl groups. And here I have the experimental triplet yield. So we go here for the unsubstituted species, species A. It has a very low triplet yield. And if we go up to E here, we have an efficiency of about 35%. 35% of the products are in the triplet state. Very interesting. How come these methyl groups, which we sort of look at, I mean, if you chem it, a methyl group really doesn't have any functionality. It doesn't pull electrons, it doesn't push electrons. It's very, very benign. How come we have more than 1 order of magnitude improvement in the triplet yield? This was not clearly understood until we did this work. So Let me try to go through some properties this molecule have. Of course, if you want to know the details, you should, of course, read our papers. So here I have a very schematic picture of how this molecule's potential energy surfaces looks like. And now we're looking at the ground state surface and the excited state surface. First of all, the 1,2-deoxyethane molecule has higher energy than its dissociative product, which is 2 formaldehyde molecules. And while we're here, I would like you to pay attention to that the carbon here is sp3 hybridized, whereas over here it's sp2 hybridized. There's a p orbital sticking out of the plane here, and there's the same here on the oxygen, and that forms this double bond. Anyhow, this dissociative reaction goes through a transition state when you break the oxygen-oxygen bond. And as you have done that, you now want to break the carbon-carbon bond. You end up in the energy landscape on a plateau at which the excited state surface is very close to the ground state surface. At this point, you can have a non-adiabatic process and actually produce these two species, one formaldehyde in the ground state and the star here indicating one formaldehyde in the excited state. This is the guy that's going to radiate down. What's even more interesting is this guy is going to be in the triplet state. This one is in the ground state, so that's obviously a closed shell molecule. So this one is still a singlet. So how do we end up getting over here? We're going to look at this. We're going to use an electron structure theory, which is a complete active space self-consistent field method, in which I'm going to, for this molecule here, I'm going to distribute 12 electrons in 10 orbitals, and I'm going to use a rather saturated basis set. This is a triple zeta quality basis. So this is what we're going to use to describe the electronic structure of the molecule. We're going to do molecular dynamics to simulate this process, and we're going to do Borin-Oppenheimer dynamics. So we're just going to do dynamics on the ground state surface, and from these dynamics we're going to get information on whether or not we're spending any longer time here at what something I call is an entropic trap. My brother is calling here. I have to tell him that I'm calling him later. Okay, fine. Then we're going to do the non-adiabatic dynamics, where I'm actually going to allow the molecule to propagate on the excited states, ground state surface, to jump over to the excited state surface and then back again. Yeah, and all of this is done with the Open Multicast projects program. Now, an important thing here for this process is it's determined that this transition state here is the limiting one. And when we're going to do the dynamics, we're actually going to start our dynamics from this position here, from structures at this point. We're not going to do dynamics starting here and hoping that some trajectories are going to go up and over. We will start all our trajectories. The initial conditions is we're starting from the transition state, And we're giving it a small push of about 1 kilocalorie per mole kinetic energy going in this direction. And then we do a Wigner distribution of the other vibrations and generate 150 trajectories. And the thing we would like to answer from these calculations is, what happens at an entropic trap? Now, what is an entropic trap? Well, you know that an entropy trap is like a bowl. If you pour water in a bowl, it's going to stay there. It's trapped by the enthalpy. It has to get over the corners in order to escape out. An entropic trap has to do with the dynamics of a species is lost in a containment that does not necessarily have a bottom. So take your bowl and make a hole in it. Now, if I take a marble and place it in the bowl, it's just going to drop out through the hole. However, if I put the marble into the bowl such that it's going around, like in Monte Carlo, it's going to take a while for it until it's lost its kinetic energy and found a hole. That represents an entropic trap. So whether something is contained in space can both be a fact because of the enthalpy, but it could also be caused of the entropy. And up here we have an entropic trap, and we're very interested to see what happens here. Is this the place that explains why chemiluminescence is like it is, and why we get these fantastic increases in the triplet yield? Let's look at some previous work. So we started to look at this molecule. So we have it here, the two green here are the two carbons, and the two reds here are the oxygen, and we designed a small orbital model, because we're going to have what we're going to have. We're going to have that we're going to break this sigma bond. So obviously we need the orbitals that describe the sigma star here. We're going to break this sigma bond. So we need to have that too in the active space. And then we have two lone pairs sticking out on these oxygens that can form a pi and a pi star orbital. So this leads us to a situation where we're going to end up with these type of orbitals. So we have two electrons here, 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 here in the sigma, but then we have more orbitals than electrons up for the oxygens, and here we can distribute them as follows. We can have the two electrons as we break the bond in these two orbitals. That would correspond to the ground state. But we could just as well move a lone pair electron into either this one or into this orbital, producing these two electronic configuration, or we could move two of them in. Now, this is the active space we designed, and now we're looking here at how these molecular orbitals, the natural orbitals, look like at the reactant position and at the transition position. So we start here at the reactant. We have, and now it's the carbon here and the oxygens here. So the picture is reversed from us down here. So we have two electrons in this orbital, no electrons here. We have then the pi lone pair, and oh, sorry. This is the sigma oxygen and this okay, we're just going to break the oxygen here, sorry. Then we have the two lone pairs. As we get up to the transition state, we see that the sigma orbitals have developed into orbitals that looks like just p orbitals. So we have the pi here have become a p orbital over here and a p orbital over here. And this sigma, the antibonding sigma, have now developed into two essential localized p orbitals. And we also see from the calculation that the energies of these orbitals are very similar. So distributing the electrons any of these ways really doesn't make much energy difference. And that explains why the excited state has this energy that is very similar to the ground state. So here's a picture, schematic one of the chemical reaction. So you start with 1,2-deoxyethane molecule here. It gets hot and it decides to break the weak bond, which is the oxygen-oxygen bond. So it does that. You get up to the transition state here. If you continue to rotate the molecule, because the way you break this bond is not like you're breaking it like this. There's a sort of a vibration in the plane that eventually breaks the two oxygens bond that you're still rotating around the carbon-carbon bond. And if you continue that rotation, which is something dynamics tells you would do, you would continue out here on this turquoise surface, which has just actually happened to be degenerate in energy with excited state surface, which is represented by the red surface here. On the ground state surface, if you make a reaction path calculation, you will have an initial twist, and after that you're going to have a carbon-carbon elongation. And that would correspond to the green arrow going down here, and you would produce two formaldehyde molecules in the ground state. If you rather continue the twisting motion and eventually allow that vibrational energy to be redistributed to the carbon-carbon stretch, there are several ways you can exit this surface and get out such that you, on the excited state surface, is producing one formaldehyde molecule in the ground state and one in the excited state. Let's proceed. So we have done calculations then using these active space calculations with this rather sophisticated basis set, and we have done multi-state cos-2 calculations. And we have looked at the energies at the characteristic points on the potential energy surface. And here we're getting the first answer to why it's the triplet manifold, the triplet yield that is so large and not the singlet yield that is so large. And so we start here from the reactant, and this point here represents the first transition state where we break the oxygen-oxygen bond. At this point now, the excited states are starting to become degenerate in energy, and also you can spin couple the unpaired electrons differently. You can either do it as a singlet, and the lines here on this side represents the potential energies of the singlet state. But you could just as well do it, couple the electrons as a triplet, and Hund's rules tell you that should be slightly lower in energy, and indeed that's what we see. So if we would have a singlet reaction, we would go over this first barrier, then there's a second barrier where we're going to break the carbon-carbon bond, which is higher in energy than this activation energy going from here to here. So if you did experimental calculations, you would then anticipate that this is the activation energy, but they really did this very good work, and they showed that you don't see these singlet excited states. What you actually see is the triplet excited states separating out. And the reason that occurs more frequently is because this barrier here is about the same as this barrier over here. So more or less the same energy. Now, we have the black curve here. We did it initially, the calculations using the cos-SCF path. So that's this curve here. And here we see that the barrier for the triplet state is still higher than the barrier here. Then we say, well, maybe we need to do cos-PT2 structures rather than cos-SCF structures. And that sort of reduced the energies in general a little bit, but not too much. Well, could it be that the vibrational energy correction makes a difference? And much to our surprise, it does that a lot. So you get these lines moving down here, these lines moving down here, and then if you put in the temperature effect, it moves down even further. So the initial ab initio result didn't tell you the full story. You need to compute the barriers using dynamics in order to understand that they are much lower than what your initial ab initio calculations told you. And now with dynamics, we see that the first and the second barrier are almost equivalent in the triplet manifold, whereas in the singlet manifold, there's a considerable energy difference of about 8 kilocalories, such that definitely, in order to have a separation over here, this is the bottleneck, whereas here, there's really no big difference. So that yes?
May I ask a question?
Yes.
With respect to this? I see here two different activation energies for the triplet and for the singlet and the triplet manifold.
Yes.
My question is, you calculated this, and when I understand this right, what should be observed in the decomposition of these dioxydanes would be a different activation energy for the formation of singlet and triplet
Yes.
states.
Yes.
So that's right. So
And in the experiment, you observed an abundance of triplet excited state, whereas you were orders of magnitude lower of the singlet excited state.
yeah, I understand, but there were works in the 70s, 80s of the last century where people tried to differentiate this, and for some reason we also worked more recently with this. And what is found in general is for dioxydanes, there is no difference in the activation energy if you have a triplet and a singlet state. Of course, this was not done with the dioxydanes, the unsubstituted, because that's much too unstable.
Yeah.
You have exact measurements. Yeah, and so the experiments in this case do not agree, or the calculations do not agree with this interpretation. But that does not mean, of course, I don't know what is right. Just people couldn't find it, and there were some works, one by Turo, another one by Schuster, I guess.
Yes.
Dioxydanes and dioxydanomes. And we have a work together with Borin when he was in Sao Paulo. which appeared in RCS advances. And we worked on the spiroadamantioxeteinone. And in this case, we found experimentally a very high difference in the activation energy. This is the only case where there is a reasonably high difference, which is, if I remember well, as huge as almost 5 kilocal, which is very high and which would be similar to your calculation. But for dioxetanes, the experiment could not reproduce this. Just to mention it.
All right. Let me proceed. So let's start now presenting the results from our recent study on this, doing dynamics. So here I have a typical trajectory represented. And here we have snapshots of the molecule at different times after we have left the transition state. And over in these graphs, I'm depicting the following internal coordinates. So we have A here is the angle between the oxygen, carbon, and the carbon on the other side. That angle is presented here as a function of the time along the trajectory. We have the coordinate B here, which is the carbon-carbon bond distance. And up in this panel, we're representing the bond length. The carbon-carbon bond length is this red curve here. We have also the dihedral angle, oxygen, carbon, carbon, oxygen, represented here. And these snapshots are from a trajectory in which we get a carbon-carbon bond dissociation immediately. As we can see here, that as the trajectory develops, at some point at about 100 femtoseconds, the molecule decides to dissociate. And the carbon-carbon bond distance gets longer and longer and longer. At the same time, the oxygen-carbon bond distance, which is more or less constant until that point, gets shorter, but it starts to oscillate like this. And in that respect, as the fragments separate, the oxygen-carbon bonds get vibrationally excited. And that's the oscillation you see here. Also, this trajectory, as I told you, is induced by the dihedral angle. And it will continue to rotate as they separate. And that's what we see here down in this panel, where we see that we're starting with a dihedral angle, which is rather small, since we just recently have broken or pushed the oxygen atoms apart. But then the two different fragments just continues and continues to rotate. So we see here the angle is increasing. And here we see that this bond angle here originally increases, but then goes down. And that's a reflection of that the molecule changes the character. In particular, the carbons here go from being sp3 hybridized to being sp2 hybridized, with, of course, a small oscillation. But for a successful dissociation to take place, we need that several of these internal coordinates work together. We need that the oxygen-carbon bond distance is getting shorter at the same time as the carbon-carbon bond is getting longer. we need that the dihedral angle continues to extend. And also we need this angle, the A angle here, to be in such a phase that as we pull the carbon-carbon bonds apart, that the angle is such that it pushes the carbons over to be sp2 hybridized. Here are potential energy surfaces done for, we have here fixed dihedral angle, so that's the D angle here, and on this axis we have the carbon-carbon bond. And if we freeze these and re-optimize all the other coordinates, but we sort of fix also the carbon, we take this, we take all the other structures to be fixed. Apart from that, we're varying these here. We get sort of a snapshot of the effective potential energy surface for these coordinates at the different times. And we see here, for instance, that initially it looks like when we do the rotation here, that you should be able to sneak out here. But when we get down at this point, at about 65 femtoseconds, we are here, we see that the vibration here is such that it's out of phase and it's not pushing the carbon towards the sp2 hybridization. And now as we approach this point, there's built up a ridge here, which forces the trajectory in this direction. And as it progresses there, this angle now starts to change and we find our way out. So this to some extent represents an entropical trap. It seems like when we're standing over here, we're not bound, but if we just arbitrarily walk out in this direction, a barrier is going to be built up and we're going to bounce back. In this diagram, we have put out what we call the dissociation time. We selected a particular time to say that once a particular carbon-carbon distance, and we said that once this is achieved, we have dissociated. This is, of course, an arbitrary selected distance, and we just to verify that it makes sense, we played around doing all these calculations with different distances. And as long as you have a distance that truly represents, the chemist would represent as a broken bond, you hardly see any difference from the dynamics. Anyhow, we see here that every dot here, every plus here represents a trajectory, and when it achieved this dissociation criterion, and we have here the time the trajectory took to get to that point, and here we have the fraction of trajectories that have achieved dissociation. So here we have all of them, and we note that typically a trajectory starts to dissociate as early as after 25 femtoseconds, which is sort of an interesting number because that's the frequency more or less of a carbon-carbon bond vibration. And some trajectories take as much as 140 femtoseconds, and on average about 59 femtoseconds for a dissociation. The trajectories that come out here and dissociate early, typically, if we look at the carbon-carbon bond distance as a function of simulation time, will look something like this. You will have a small, maybe the carbons going towards each other and then they dissociate. So that's what this curve represent. And the green successful dissociation is, we should understand that as the carbons were going out, we had this favorable oscillation of the carbon-oxygen bond getting shorter, and also we had that the angles, the A angles, simultaneously were straightening up the molecule, forcing the carbons to go over to sp2 hybridization. Here is another such graph for another trajectory, actually trajectory 117, where the bond distance, the carbon-carbon bond, first increases, then it's repelled back. It tries another time, it's repelled again, and only on the third attempt it dissociates. And probably we have that the carbon-carbon bond stretch was out of sync with the other coordinates at this and this time of the simulation, forcing the molecule back because it built up one of these barriers for this dissociation. And what we have noticed is that there are geometrical conditions that needs to be fulfilled. So here we're looking at the dihedral angle here for the different trajectories, each at the point of dissociation. And so each point here represents the angle the molecule had, the dihedral angle that particular path had at dissociation, and also we plotting here the oxygen carbon carbon. So this angle up here, which to some extent controls the sp2 sp3 rehybridization of the carbon. And we can see sort of a clustering for the frustrated paths, those that didn't dissociate. So this, okay, the red dots, of course, are structures that are found either here or here, not here, of course, but here or here, whereas the green dots are typically at the point here along a successful trajectory. First of all, we see that the dihedral angle has to be larger than 55 degrees. So the two oxygens needs to get away from each other. If they do, we're getting a green dot. So if the system still is close to planar, we will not have a dissociation. And also we see that if the oxygen carbon carbon bond distance is too large, we are not going to get the favorable rehybridization of the carbon. So we can more or less see here that you have to be in this part of the phase space to get a favorable situation for a dissociation. So we did this first for the species with no substituents. Then we started to pull the methyl groups on the species. So here we're starting with the unsubstituted species. Species B, we're changing one of the hydrogens with the methyl group. We redo the simulation. And we got something that didn't look much different. And this is to some extent expected because there's only one heavy methyl group. The rest of the molecule can move around as before, so it shouldn't affect things. We have two methyl groups, and in C, the two methyl groups are substituted in on the same carbon. So the other side is still as flexible and still as light as before. And again, we get a slightly increased lifetime, but the big picture is no big change. Now with D3, we have 2 methyl groups over on one side, and now we put one with a bit of weight on the other side too. So now the motion of the carbons getting away from each other is affected more. And indeed, we increase the lifetime with about a factor of 2. And as we add the 4th methyl group, we're getting even a longer lifetime. So there is a significant increase in the lifetime, slowing down the whole dissociative process if you introduce methyl substituents. And this could be understood either from that there's sort of spatial abstraction, making the molecule not getting the oxygen and the carbon bonds to reach the favorable configurations for dissociations, or it could just be that you're adding mass to the system that makes it slow down. Over here in this graph, we have now looked at the different substituted 1,2-deoxyethane molecules. So we have A, B, C, D, and E here. And in this, I'm plotting the ground state dissociation half-life times. So that's these guys coming out here, versus the time it's on average take these different species to reach an angle that is more than 55 degrees. And we see there's a very nice, almost linear correlation between that. You need to reach that angle before you get a dissociation. And it's sort of, you picture that, yes, this dissociative motion getting more and more difficult or slower if you put heavy substituents on the carbon, because now they can't turn around as fast. They need much more kinetic energy to do it as fast as did it before. We did make an experiment, which you can't do in reality, and you could ask yourself, how much does it have to do with that the methyl group is heavy, and how much does it have to do with the very fact that, for instance, that the methyl group have a longer carbon-carbon bond than the hydrogen-carbon bond it replaced, such that the heavier mass ends up a way bit out, and also the methyl group extends in space. What role does this make? So we redid the simulations with a fixed carbon-hydrogen bond distance, but the hydrogen, we gave the same mass as the methyl group. So if we look here, I'm trying to represent the result of that. So here we have the E case. We have 4 methyl groups. That's this curve here. The red one is the A case. It's this guy up here. And this curve here is a simulation where all the 4 hydrogens have the mass of the methyl group. And we see that the mass plays an important, significant role, accounting for about 50% of the difference between non-substituted and substituted species. So partially, this retardation is a pure mass effect. What about entropic trap? Well, we argue that the longer you stay in the entropic trap, the more likely it is that you're going to populate the singlet excited and the triplet excited state, such that we say there must be a correlation between the lifetime in the entropic trap and the yields you get. And here we have a nice graph in which on this axis I'm plotting the experimental chemiluminescent yield as how much triplet is produced, and I'm plotting that against the results from the simulation, which is the calculated dissociation half-life time, and we're using this equation to relate the two entities with respect to each other, and we're getting a very nice curve. That we have the dots here that can be fitted to a very nice function that looks like this, which is sort of in line to what you would expect. So clearly the experimental results are consistent with exactly the argument that the lifetime you spend here is the crucial thing. The longer time you spend there, the more you increase the probability that you're going to have a non-adiabatic process going up on the excited state surface. So to verify this, we did some more dynamics, and now we did with surface hopping. And there's not much more to say than we have here the dynamics when we only did the ground state dynamics. If we introduce the effect of surface hopping, we see in general that the lifetimes increase, the half-life times increase when the molecule can go up on the excited state surface and come down again and dissociate. And here we plotted the numbers of ground state. So we have the ground state simulation only here, and here are the four singlets with the four singlet states looking at the half-life times, and it again fits very nicely to a curve which is consistent with experiment. Of course, what we're missing here in our simulations is we don't have any dynamics such that we can populate the triplet surface. And that, if I remember, Jajun and Beijing have done simulations that, again, supports these results. Here are some results on doing the non-adiabatic simulations. So we had here the blue curve was ground state. Here we see the same curve using the non-adiabatic dynamics. Also, we can see again here that this particular angle is very important for the dissociation. And just we have this guy here. This is actually the structure you would get if you did just follow the minimum energy pathway on the potential energy surface. You would get a completely wrong dihedral angle. Down in this graph here, we're depicting the energies of the different states as the molecule evolve. And here we can see exactly what I was saying. We're starting here at the transition state on the ground state surface. And as the molecule now evolves with time, the excited state surfaces are getting close in energy to the ground state surface. And in this regime here, you have potential for non-adiabatic processes taking place. And particularly over here, we see this green state, the S1 state, is extremely close in energy with the ground state. But here, of course, in our simulations, we continue down on the ground state surface and dissociate. And of course, then the S1 state goes up in energy. Also here we see how the population of the different states evolve with time. And we see here again in this intermediate regime where we are in the entropic trap, the probability of being in another state than the ground state increases and is not zero. It's a non-zero. So I'm getting to my conclusion. I hope that, or we think that these simulations have sort of given us an understanding on why these intriguing experimental observations with a very big change of the triplet yield, why that is taking place. And also we have shown that this is initiated by a methyl group that sort of is a very innocent substituent, but to a large extent, just the mass from it slows this dihedral rotation, and that much of the effect you see in the experiment is a simple mass effect. So I think we believe that we have sort of understood why nature is doing as it does, why these true molecules, which are much larger, why they need to be large, and nature have designed the substituents to optimize the chemiluminescent effect. And it also helps us understand that if we're going to design artificial systems, slowing down the dynamics, making a molecule live a longer time in the conical intersection or in the tropic trap where the states are nearly degenerate is a very important feature. And with that, I thank you for your attention. I have some more figures here, but that's just bonus material if somebody asks some questions. So thank you very much. Are you still there?
Yes. Thank you, Roland. It was a very nice presentation.
Let's see now. I need to get you up. Okay, fine. Thank you.
Thank you. And it's very nice to see that to run the calculations it's very tricky. It's difficult, this kind of calculations. But more important than that is to have the chemical knowledge about the systems and the reactions. Otherwise, it would be impossible to draw these conclusions. So to run the calculations are necessary, but the chemical knowledge is essential. Thank you very much.
Thank you very much.
And
any questions?
I would have one.
Yes, please.
So, hi Roland. Thanks for the very nice talk. My question would be whether you saw in the trajectory surface swapping any trajectories that actually picked in the excited state, because that's what you showed in the beginning, that there is a certain chance that at this conic intersection you just stay on the upper surface and then relax to some metastable state from where you can luminesce.
Could you ask that question again, please? My brother just tried to call me again.
No problem. So in the beginning, you showed that you have this certain chance that at the conical intersection, you just switch to the upper state, and then from there go to some singlet or triplet minimum from where you can emit. Did you see anything like that in the surface swapping simulations?
Well, as our simulations didn't allow any interstate crossings. So our hypothesis was that rate is proportional to the time you spend in the entropic trapping. So we're saying that's the same thing. And I think our graph that sort of correlates the yield with the time spent in entropic trapping is consistent with that.
Okay, so you say that the longer you're in this region, the more inter-system crossing would happen, but you don't simulate that. And
Yes.
once you do that, you go to the T1 state, and from there you can emit. But there is nothing similar for the S1 state? Or is this too short-lived?
The S1 state, they have this additional barrier they have to get over to break the carbon-carbon bond. And they don't have enough kinetic energy to do that. So you're getting into this conical entropic trap. The singlet excited state is bound for all practical purposes. The only thing it can do is bounce back, go down on the ground state surface, and dissociate.
Yes, sure.
While the singlet excited state is slushing around there, you could have spin orbit coupling and populate the triplet surface. Here, there's no barrier for further dissociation. And we're just claiming that sort of the time spent in that entropic trapping, you will have a constant velocity or speed at which the transition takes place.
Yeah, that makes sense.
So it's like a tub. You pour in water, you plug out the hole, and it really doesn't. I mean, the speed at which the water comes out is proportional to the time, not how much water you have in the container.
Yeah. Okay. Anyway, it still sounds like an interesting problem to do with intersystem crossing surface hopping.
I think Judge Liu in Beijing just did that a year or two after this.
Okay, then I will have a look. Thanks.
Yes, be my guest.
Please, any other question?
Roland,
Yes, sir.
very interesting work. I understood just a small part because the theoretical part I don't understand. So I just try to understand what we can take out from this. And I have first two questions. The first one, a very simple one. The derivatives C, which is with two metal groups. As of course you know, there are two other derivatives.
I know.
Could use. Now my question is, did you try to calculate this? Because this could be an interesting information. If it's different, if the two methyl groups are in different carbon.
Yeah. I don't remember if Morgan did that. I actually pointed out that I would like, and I think she actually did, but since there were no experimental results to correlate that with, we didn't present it.
No. There are experimental results.
Well, at the time we did this, we only had this original paper to go with.
Yes, but there it is.
I suggest you contact Morgan Vacher and ask her about this. But I'm as far as I remember, if you put it on both sides, you get a longer lifetime as compared to if you have them at the same side. And I told her this would be really a crucial test on our hypothesis if it did predict this in accordance with experiment. And I hope you can tell me that you get a higher triplet yield if you have them on the different side than on the same side.
Yeah, it's a little bit higher. It's not if you consider the experimental standard deviation. The standard deviation of the experimental data, it's within. But in all cases where I measured this and directly compared the 3,3, which is the one you calculated, and the 3,4, where is a cis and a trans, yeah, always the 3,4 had higher quantum yields, a little bit more stable also.
Right, yes.
Specifically, if you have the cis derivative, this is more stable and has higher quantum yields.
Yeah.
Might be interesting. Maybe I already asked Morgan, this and the Congress in France, where you bioluminescence Congress, where you didn't come. Maybe if she had presented this there, I asked her, but I don't remember the answer.
I wasn't there.
One other thing, in all your lifetime calculations, as far as I saw, your reagent is a biradical, where the oxygen-oxygen bond is already cleaved. Yeah.
Say
lifetime calculations, you part from the compound, not from the dioxidane, but you part from the compound where the oxygen-oxygen bond is cleaved, at least as you show this.
I will start from the transition state. Yes.
No, it's a biradical. It's not a transition state, as far as I understand. Oh, so
yes.
My question first, what I understood from your from the pictures you showed, that it would be from the biradical, and my question would be: can you calculate it from the dioxidine and to allow only a partial opening of the oxygen-oxygen bond? I asked you this because that's what we thought would happen on the basis of our initial data, of our experimental data, which would be a what we call a concerted decomposition, where the oxygen-oxygen bond is cleaving, but the carbon-carbon bond also is cleaving already, without the formation of a real biradical in an energy minimum. Yeah.
Well, I have a hard time to see that this is going to happen. The oxygen-oxygen bond is a very poor bond, whereas the carbon-carbon bond is a very strong bond. There's nothing that sort of argues for that those two bonds would come apart simultaneously. Of course, if you did tons and tons of trajectories, there would of course be some trajectories which would represent this, but I don't think it's representative for the process in general.
Okay.
Breaking both bonds in ours simultaneously in our simulations corresponds to a double saddle point.
Mm-hmm. Just to insist one more time, I don't believe that it should be simultaneously. Simultaneously, I understand that both bonds cleave in an equal manner. So you just open, but you can open it differently.
Yeah.
Bond.
You have sort of 50 shades of gray between something that is completely concerted and yes. Of course, when you start to do dynamics, you're going to get more and more gray or more and more white, whatever you like it. But it's the oxygen-oxygen bond that have to come apart first.
Mm-hmm. Okay. That's okay. Thank you.
Oh, you're welcome.
More questions? So, if nobody wants to ask any other questions, I thank you, Roland, again.
Thank you very much.
This opportunity, and I hope to meet you again soon.
Yeah, thank you very much for organizing this and inviting me. It's been a privilege.
Thank you very much. And we will keep talking about the other projects. We talk at the beginning about MOCAS workshops or things like that.
Yeah, yes.
So
I think we have to wait out the pandemic first.
Yes, but I think it will be solved. At least for Igor, I think it's already solved. Don't you? Don't, Igor? Igor? No? Okay. So, thank you very much, Roland, and see you soon.
Thank you very much, and see you later. Bye-bye.
Bye-bye.